So I'm going to get started on this discussion. Go ahead and kill the lights. I've worked on this PowerPoint for a long time, and it's dealing with stuff that's really, it's kind of outside of the typical area of expertise for most architects. One that I know of is not that way, but the rest of us are, right? Remember, we are engineers that don't like math. But in order to kind of understand the complexities of how a building sits in its environment and how heat goes through a building and back out, in and out of a building, we kind of got to understand some of these concepts. Now, normally these concepts would be covered in far more depth in a physics class. Unfortunately, our physics classes, because they articulate to so many schools, don't have very much of this in them. They cover this stuff very quickly, briefly, in 2 or 3 class sessions. So I'm going to try and give you guys this kind of synopsis of stuff. It's mostly about understanding concepts and less about the mathematics involved in doing any of this stuff. So try to focus on that. Also understand, I want to take a moment and say I did this as best I could, but there's stuff that can be a little bit confusing. I tried to present it all in as simple and clear a fashion as I could. Okay? All right. Totomi, you're checking to make sure I don't go over 12 minutes, right? Okay. So the key thing right now that we're going to look at is understanding heat transfer. So we have had 2 previous lectures on energy and heat. Okay? So the first one was what is energy? The next one is what is heat, or what is heat energy. So now we need to take a look at understanding how heat moves, how heat energy moves. Okay? So, not clicking. So the very first thing that we got to get to the bottom of is this kind of strange thing about mass, matter, weight, and gravity. Right? So people have been weighing stuff for centuries, right? So people, back in the Renaissance, people were weighing things, and science was sort of being born, right, or reborn. And the Greeks and the Mesopotamians and the Egyptians all had ways of measuring stuff, right? But most of those cultures or those societies weren't really aware of much dealing with space, right? I mean, they probably couldn't conceive of a place where there was no gravitational pull, right? When your whole world, your entire frame of reference is the Earth, right? Then the gravitational pull of the Earth becomes an accepted thing that you don't think about. Okay, so we use the word mass to talk about how much matter is in something, all right? Matter, again, is anything you can physically touch, including air. So if I'm swiping right now, I'm hitting millions and millions of particles as I swipe my hands through the air. Okay? Everything that we come into contact with has some level of matter to it. All of our solid things, at any rate. We're not solid, it's all of the stuff we can come into contact with. On Earth, we weigh things to figure out how much they weigh. Okay? So, all right. So we take something and we weigh it, and it's like, okay, this thing weighs 10 pounds, or this thing weighs a kilo. This slab platter of carnitas is 1 kilo. My favorite reference to kilo. Right? The amount of mass that something has is not directly related to weight. All right? So I give this little example. So imagine I take a balloon and I blow it up to the size of my head, or your head, or your head, or your head, right? So the volume of the balloon and the head is about the same. But the density of the balloon, since it's empty, is very low, right? The volume of the head is much heavier, much denser. It has more stuff in it, okay? The difference between mass and weight is the weight is determined by how much something is pulled by gravity here on Earth. Okay, and so scientists had to come to a point where they realized that, wait a minute, if the gravitational pull of Earth is what we're assuming, right, measures mass, then we've got a problem, because what happens when we get to the moon or to Mars? How many of you have seen pictures of the men landing on the moon? Anybody? Or video? When they walk, right, they fly through the air and they eventually come back down. And that's because the gravitational pull of the moon is substantially lower than the gravitational pull of Earth. Mars is a smaller planet than Earth, so the gravitational pull on Mars is going to be lighter than it is on Earth. The gravitational pull of Jupiter, right? Jupiter's a massive planet, it's huge, would be crushing to a human being. So those are things that you guys got to kind of take into consideration. So here's some notes on mass and weight. So what is mass, right? What is mass as compared to weight? So the mass is the volume of an object, okay, multiplied by its density. So this is something you may have learned in high school science class, okay? Mass, the amount of stuff that's in a thing, okay, is completely independent of gravity, right? Remember, gravity is the weight of something based on the gravitational pull of Earth. Most of the time, for scientists, they express the mass of an object in kilos or grams, right? So the scientists sort of took over this thing. The scientists gave up on pounds and ounces and stuff like that, and they instead went with SI measures or SI units. And so they said, okay, well, we're just going to take the stuff that we've already know about on Earth and make that the standard. So kilograms and grams are going to be what we use for density and mass of an object, okay? And that causes confusion because we've taken the SI units and made those the standard by which we're going to measure mass, which we assumed was the thing that was pulling on it on Earth, the weight of it on Earth, and it really wasn't, but we said, okay, since we found out it is, we're going to just use this. And it sort of left pounds and ounces out, which is what we use in the United States. All right? So it's key to understand that the scientists are going to use kilograms and grams both as a measure of mass and weight. Okay? For the purposes of this course, for us non-scientists, we're going to use the number value for mass the same as its weight. And I'm going to go one step further and I'm going to say, screw it. We are going to say that pounds and ounces are equal to mass, just like kilos and grams are equal to mass. So more continued notes and some examples. So the measure of the object multiplied by how dense it is going to give you, right, the mass of the object. And so imagine a hollow ball of metal and a solid ball of metal. They weigh different on Earth, right? So if you take those up into space, do they weigh different? Not really. You can't feel them because you let them go and they just... And then they would get to one of those laws, objects set in motion tends to stay in motion until acted upon by another force, right? Remember that one? That was from high school. So on Earth, the hollow one, right, weighs a lot less than the solid one. So we can really tell that the solid one is much denser and has more mass than the other one. When you get to space, you wouldn't be able to tell the difference. You'd look at them and they'd like, hey, that one looks like a ball of metal and that one looks like a ball of metal, the same color and everything. Okay? So it doesn't change the fact that the solid one has more mass than the other one. Okay? Now we're going to go on. Now that we've established what is mass, okay, that mass is the amount of matter in something, we're going to go on to something called relative density. Okay? So relative density is the mass of the object divided by its volume now. Okay? So let's just say I have a piece of 2x4, this big, and I have a piece of steel, just the same size, and I have a piece of styrofoam, just the same size. Right? So the measure of relative density of those three things is going to be how much mass there is in each one. The steel has the molecules much more closely together, right? And there's a lot more of them, and they're heavier than the wood, which in turn does the same thing to the styrofoam. So 1 cubic foot of water. So cubic foot. So imagine a block of water sitting in a plastic square bag, right? 1 block of water weighs 62 pounds. And the way that we express that is 62 pounds per cubic foot. And this is kind of the way it's written. Okay, now imagine another block of copper, right? So they're sitting right next to each other. That block of copper is going to weigh 559 pounds per cubic foot. There is a lot more matter in the block of copper than there is in the block of water. Okay? All right, so I'm going to pause this or stop this video so I don't go too long, and we'll start it up again in the next one.